Hi everybody, this is Mrs. T giving you a little KSP introduction. Mrs. Temanello, I teach at Calhoun High School in Merrick, New York. First thing, when we talk about KSP, KSP is a special type of equilibrium called the solubility product constant, and it's also about solubility. So this is going to be about salts that are very, very slightly soluble. They are soluble to just a very small degree. So for example, it's only going to have one value for a solid at a given temperature. And if we talk about solubility, again, we're talking about an equilibrium position. So we're talking about an amount or a favoring of products or reactants for our equilibrium position. And if we talk about this compound Bi2S3, which would be bismuth sulfide, or when we put it in solution, there's going to be a certain amount of bismuth ions compared to sulfide ions that are able to be dissolved. And that's going to be based on the value of the KSP. So again, because of the fact that KSP is only allowing to have aqueous and gases, because solids are never allowed in the KSP, the Bi2S3 actually drops out completely. So it's as if it's Bi plus 3 squared, because that was its coefficient, S 2 minus cubed over 1, because this wasn't there. Because it's a solid, it just drops completely out. So our KSP expressions are not going to have denominators. For this particular substance, the KSP is going to be equal to 1.1 times 10 to the negative 73. That's really small. So this is not very soluble at all. It's extremely, extremely insoluble in water at this given temperature that we're talking about. So when we're talking about KSP, again, this is going to be the concentration of the bismuth ions times the concentration of the sulfide ions raised to the power of their coefficients is always going to come out to that amount. That's the maximum amount that we can get to dissolve. So whatever we put in for one, the other one will multiply by it to get to 1.1 times 10 to the negative 73. We can use this expression to find what's called the molar solubility. The molar solubility is the X value, or sort of the maximum molarity of this compound that will be able to dissolve. And doing a rice chart or an ice chart for our KSP is going to look a little bit different, but a lot of it is going to look the same. So we're going to set up first our reaction. We're going to do our initial, our change, and our equilibrium amounts. And we're going to set the equilibrium amounts again equal to the K expression. So since this is a solid, it actually doesn't exist in our rice chart. And since these start out before the substance dissolves as 0, that means that we're going to have to shift towards products, making this a plus 2x and this a plus 3x. Because remember, it's coefficient x, coefficient x. We're adding products because as this dissolves, we make ions. When we first put it into water, it's a solid. As the reaction reaches equilibrium, some of the solid makes aqueous ions. We read down 0 plus 2x, 0 plus 3x, and we put these numbers in to the equilibrium expression. So I'm going to put a 2x in here and a 3x in here and set it equal to 1.1 times 10 to the negative 73. So 2x whole quantity squared, 3x whole quantity cubed equals 1.1 times 10 to the negative 73. Be very careful when you simplify these, because this is not, well, this one is 4x squared, but this is 3 cubed times x cubed. which is actually 27x cubed, and still equal to 1.1 times 10 to the negative 73. When we simplify this, we wind up with an x to the fifth, and 4 times 27, we wind up with 108x to the fifth equals 1.1 times 10 to the negative 73. We're going to divide both sides out by 108, and then take the fifth root. Remember, math function on your calculator. You can do math and you can scroll down and make this be the fifth root of this expression. Once we do that, our x actually comes out to 1.0 times 10 to the minus 15, and that is a molarity. This here is called the molar solubility of Bi2S3. This is the maximum molarity, the maximum number of moles of Bi2S3 that we can get to dissolve in 1 liter of total solution. If we want to do another example, for example, they might say to calculate the solubility of silver chloride in water and give you a Ksp. So again, we'd need to start from the beginning here. No, I don't want you to see it. Sorry about that. So we'll get there. But if we want, first we need to know, or we need to remember, that Ag has a +1 and Cl as a -1. So when silver chloride goes into water, it makes Ag plus aqueous and Cl minus aqueous. So again, since this is solid, it drops out. The Ksp equals Ag plus times Cl minus. They're coefficients of 1, so the powers or the exponents are 1 also. When we first put in our silver chloride solid and we have nothing dissolved, the concentrations of the ions are each 0 for our initial. They each go up by coefficient x, which is a 1, and so at equilibrium, it's an x. And what that means is that for our Ksp, 1.6 times 10 to the minus 10 equals x times x, which means that it's equal to x squared, which means, I guess I really don't need the 2 there, which means that we are going to just square root each side to get our x. And again, remember, when we get our x of 1.3 times 10 to the minus 5, this is called the molar solubility. That means that we can have a 1.3 times 10 to the minus 5 AgCl solution. This is the maximum concentration of AgCl that we can get to dissolve at this temperature that the K is good for. If we want to calculate the solubility of silver phosphate in water, who has a Ksp of 1.8 times 10 to the minus 18, now we're going to need to find the formula for silver phosphate. Remember that silver is a +1, but that phosphate is a -3. So when we crisscross and drop the signs, this becomes Ag3PO4. So this reaction is going to be 3 Ag plus PO4 minus 3. That means, again, remember, solids drop out. Ksp is going to be Ag plus to the third PO4 minus 3 to the first. These are initially going to start out at 0. They're going to increase by coefficient x. We're going to read down to get the numbers that plug into the Ksp expression. So now my Ksp is 1.8 times 10 to the minus 18. It's equal to 3x, because that's the number for equilibrium for Ag, cubed times x to the first. Again, be very careful with how you simplify this. It's going to be x cubed and then 3 cubed, which is 27x cubed, times another x is 27x to the fourth. And that's equal to 1.8 times 10 to the minus 18. Oops. Divide both sides by 27. Take the fourth root of each side. You can do 4 math 5. Second answer after you do this number divided by 27. Or you can do 4 math 5, 1.8 times 10 to the minus 18 in parentheses divided by 27. Either way, you're going to get your answer. And the x, I'll change the color so you can see it a little better. The x winds up coming out to 1.6 times 10 to the minus 5 molar, which means that for this particular substance, make that a little easier to see, for this particular substance, that's the maximum molarity of silver phosphate that you can get to dissolve at this particular temperature. And what I'd like for you to note is that it's actually slightly more soluble than the silver chloride. So this is 1.6 times 10 to the minus 5 molar. This is 1.3 times 10 to the minus 5 molar. But if you look, this particular Ksp was 10 to the minus 18. This was 10 to the minus 10. That's because of the number of ions that were present. Because this one was cubed, that sort of made this seem like it was less soluble. So in order to compare the solubilities, you don't just compare the Ksps, you actually compare their molar solubilities, because that's going to be the maximum number of moles of substance that we can get to dissolve in 1 liter of total solution. So this was just a little introduction of Ksp and Ksp expressions and finding molar solubility. Hopefully this was helpful. If you need any help, you'll let me know. And actually, just to move on a little bit, we're also just going to talk about precipitation. When we do have mixing of solutions, when a precipitate forms, it's going to be because of the fact that we have exceeded the Ksps. So when we make a precipitate, it's because of the fact that we've gone too far for the Ksps. So if when we put the ions into the Ksp expressions, the Q is greater than Ksp, that means we have too many ions. That means that there will be a precipitation. Now, only remember the Ksp is the maximum that you can have, so you can't actually have more than the Ksp dissolved. That's why a precipitate would form. If Q is less than the Ksp, we haven't hit that maximum number yet, so that means that everything will stay dissolved. And there are ways for us to actually selectively precipitate different ions using our solubility rules. Lucky for you, this is not really focused on the AP exam anymore. But for example, if we wanted to get barium or silver, and we only wanted to get, we had barium and silver, I should say, but we only wanted to get the silver out, chloride makes silver insoluble, but chloride does not make barium insoluble, so it wouldn't pull the barium out. The next time we meet, we will go over some more textbook questions. Again, just some little notes here. Ksp is going to just really be products. There really is no denominator because the denominator is a solid. These coefficients are going to come from these exponents are going to come from the coefficients, but you can get them if we look at our Bi2S3. That Bi2S3 made 2Bi plus 3 and 3S minus 2. So these coefficients become the exponents, and they came from the subscripts. So my Ksp for this one is Bi plus 3 squared S minus 2 cubed, and those numbers came from the subscripts. We also want to note that when we look at our Rice charts, just actually move this. So Ksp equals Bi plus 3 squared S minus 2 cubed. When we look at our Rice charts, those numbers are also going to be the numbers that go in front of the x's. So this number also goes in front of the x, so that when we plug these in for our Ksp expressions, you wind up with that subscript being both the coefficient and the exponent. The coefficient and the exponent. And if you know what the Ksp is, it gives you a little bit of a shortcut to be able to do that. So I'm just going to go through that one more time with another example. For example, for example, I'll go with the Ag3PO4 again. I can tell you right now that Ag is going to be 3x cubed, and PO4 is just going to be x to the first, because PO4 has an understood 1 here, and the Ag has a 3 here. So this is going to be 3Ag plus PO4 minus 3, which means that this winds up being a plus 3x down here. Because this is a 1, this winds up being a plus x. So that's going to be a 3x cubed, and that's going to be an x. So your subscripts of the salt ions become the coefficients of the x's in the Rice chart and the exponents in the Ksp expression. So hopefully this gave you a little introduction on Ksp. The next time we're together, we'll do this again, and good luck. See you soon.